So I'm just finishing up teaching abstract algebra, and we just did this construction method for building fields. And I thought that I would give you an idea of what that's all about. I think it's pretty interesting. But in order to do that, let's recall the definition of a field. So a field is a set F together with two commutative and associative operations. We'll call those plus and times. And in most cases, they are really just addition of numbers and multiplication of numbers. And then they have to satisfy some axioms. So first of all, there's a zero element that serves as the additive identity. Next, every element has like an additive inverse, which we'll call minus a. Next, there's a multiplicative identity, which we'll call 1. And then this is a really important one. This is maybe the most important one and the one that we'll check for a bunch of our examples. And that is, if we have a non-zero element, then it has a multiplicative inverse. So let's see that written carefully. So if a is not equal to 0, then there is an a inverse in F such that a times a inverse is 1. And if you try to look at number systems like of different varieties like the integers or other things like that, you'll notice that this is the thing that's often lacking. So for example, this is lacking within the integers because, you know, the number 2 does not have a multiplicative inverse. That would be 1/2, but that's of course outside of the integers. But that being said, if we're inside of a field, we have to have a multiplicative inverse. And then finally, we need some sort of rule for the interaction between the multiplication and the addition, and that's the standard distributive rule. So here we have a times the quantity b plus c equals ab plus ac. So the great thing about the definition of a field is it's really like the axiomatization of properties of numbers that you've seen before. So you know that addition is commutative and associative, multiplication is also commutative and associative. There's a multiplicative identity and an additive identity, multiplicative inverse and additive inverse, and then a distributive rule. But this is just putting it all together into some sort of like abstract setting. Okay, let's look at some familiar examples, starting with the rational numbers. So this pretty clearly makes a field. Notice if we've got a number a over b, which is in the rational numbers. So every rational number is a ratio of integers. If this thing is not 0, so let's say here that a is not 0, well, b is never allowed to be 0, then we can easily write down its inverse. So a over b inverse is simply b over a. And notice that just takes the reciprocal essentially. And so we all know how to find the inverse of a rational number. You just take its reciprocal, and that's what we're seeing here. And then the real numbers also form a field. So if we've got a number x, which is not equal to 0 in the real numbers, then the number 1 over x is inside the real numbers. Now, constructing the real numbers out of the rational numbers and proving that you get a field is actually pretty tricky. So we're just going to take this one kind of as a well-known fact. Next up, we have the complex numbers. And so that's going to be everything of the form a plus bi, where a and b come from the real numbers. And now let's show that we have inverses for everything here as well. So, and we'll do that by taking the number 1 over a plus bi and transforming it into the correct form. So this form where there's no I in the denominator. So the strategy for doing that is to multiply the numerator as well as the denominator by the conjugate. So this will be a minus bi, so we're only multiplying by the number 1. And that'll give us, let's see, a minus bi in the numerator, and then we'll have a squared plus b squared in the denominator. Okay, so what does that tell us? That tells us that a plus bi inverse is simply a over a squared plus b squared minus b over a squared plus b squared times I. And now we have that complex number inverse in the correct form. It's a real number plus, or minus in this case, but that's the same, a real number times I. And now we've got another example, which is an example of a finite field, and that's the integers modulo p. So very simply, we can just take all of the numbers between 0 and p minus 1, and then our addition as well as our multiplication will be done modulo p. That means we divide by the prime and keep the remainder. So maybe as a simple example here to get an idea for how this works, let's look at, let's say Z7. So 7 is a prime. Now let's look at a couple of additions and a couple of multiplications just so that we see what's going on. So notice that 6 plus 5 here, well, 6 plus 5 in the real world is 11, but if we divide 11 by 7, we get a quotient of 1 and a remainder of 4, so 6 plus 5 is equal to 4 inside of Z7. Okay, well, what if we did a multiplication? Let's do 6 times 5. Well, 6 times 5 is 30, but 30 is 2 more than a multiple of 7, that multiple of 7 being 28. So that means our remainder would be 2. So 6 times 5 would be 2. So let's maybe do one more. Let's notice that 4 times 2 is equal to 8 in the real world, but in Z7, 8 is the same thing as 1 because it's 1 more than 7. So we have that. But that's actually a really important example because that's an example of inverse pairs occurring inside of Z7. Remember, the most important property over here is that everything has to have an inverse. Well, writing that down in ZP is not super hard, but you do need something called Bézout's lemma. But doing it for small values of p, you can just kind of guess and check until you find inverse pairs, and we found one right here. So this means that, for example, 4 inverse inside of Z7 is equal to 2. And then maybe what would 3 inverse be? Well, 3 inverse would be 5 because 3 times 5 is 15, but 15 is also 1 because it's 1 more than 15. So there we have 3 inverse is equal to 5. And then we've only got a few more to check. I'll let you decide what the other inverses modulo 7 are. Okay, so now that we've recalled both the definition of a field as well as some nice examples, let's look at this construction rule. So now we're ready to look at our construction rule for building new fields out of old fields. So we're going to need 2 parts. We're going to need a field, and it can really be any field. So the ones that we've already seen before, like the rational numbers or the real numbers. For like a pretty interesting reason, the complex numbers are not a good choice, and we'll maybe talk about that briefly as we go over all of this, or the integers modulo p. And then we'll also need a polynomial where the coefficients come from that field. So I've written this as f of x is in f adjoin x. So that's the collection of all such polynomials. And the most important thing here is that that polynomial is something called irreducible, which means that it does not factor into smaller parts. Okay, so now that we have these parts, what do we do? Okay, so maybe the first thing to do is to introduce a root of the polynomial. So maybe for the purposes of this video, we'll call that root alpha. So what do I mean that alpha is a root of that polynomial? Well, that means it satisfies the equation f of alpha equals 0. Now notice, since f of x does not factor, we know that no such alpha exists to do this inside of the field. If they did, we could factor out like an x minus alpha or whatever. So that's why introduction of this root is a new object. So maybe let's go ahead and put that over here just as a thing to remember. So it's impossible for alpha to be inside of the field because, like I said, otherwise it would factor. And you might say, well, where does this alpha come from? Well, I think maybe at this stage, the best way to think about it is just as some sort of abstract symbol that satisfies this rule. And now where do we go from here? Well, let's get like a little bit more specific about this. Let's write down a form for our polynomial. let's write f of x in the following format. So I'm going to write it as x to the n minus a n minus 1, x to the n minus 1, minus a n minus 2, x to the n minus 2, minus all the way down to a1x minus a0, like that. And I guess I should say that all of these ai's come from the field. Another thing, you might say, well, why do we have a coefficient of 1 here? Well, since we're in a field, we can always multiply by the multiplicative inverse of that leading term to turn it into a 1. So since we know f of alpha equals 0, that means we can plug alpha into this expansion of our polynomial, and we get this nice equation involving alpha. And that would be alpha to the n can be rewritten as a sub n minus 1 times alpha to the n minus 1 plus a sub n minus 2 times alpha to the n minus 2 plus all the way down a sub 1 alpha plus a sub 0. And now it's maybe clear why I used minuses here. So of course I can choose to use pluses or minuses by absorbing into those coefficients, but putting those minuses here keeps everything nice and clean. So now what we'll do is form the following set. So the set will look like this. So I'm going to use the notation f alpha, or maybe f with alpha included, or f adjoin alpha, or something like that. There are lots of different words you could use. And this is going to be the set of, well, it's going to look like all polynomials with coefficients in alpha, but we're going to impose the condition that the polynomials cannot be of degree n or higher. So this is going to be like b sub n minus 1 times alpha to the n minus 1 plus b sub n minus 2 alpha to the n minus 2 all the way down b sub 1 alpha plus b sub 0. And here these b sub i's come from f. So it's a combination of objects like that. And then how does the multiplication between these types of objects work? Well, we simply just do the distributive rule, and then once we encounter something that has an exponent on alpha that's bigger than or equal to n, we use this reduction. Okay, so like I said, anytime we multiply and see alpha to the n, we replace it with a sub n minus 1 alpha to the n minus 1 plus all the way down to a sub 0, because we've imposed that condition on alpha. And that's why we don't need any power of alpha that's larger than n minus 1 here. Because after doing the product, anytime we see a power of alpha that's bigger than n minus 1, we can use this rule multiple times if necessary to get it down to a smaller power. Okay, so this is all well and good. Let's look at some examples now. So let's do some examples. So the polynomial x squared plus 1 in R adjoin x is irreducible. And I think we can pretty clearly see that this is irreducible because, well, first of all, the number I is not a real number. The number I meaning the square root of minus 1, which would be the only way to reduce this is by factoring it. But the number I is a complex number, and we can include it just as we did before, symbolically as R, maybe adjoin I. And so this is going to be everything of the shape A plus BI, where A and B are real numbers. But notice that's exactly equal to the complex numbers. So if we take an irreducible polynomial like this over the real numbers, and we take a root of that polynomial, in this case we know what the root is, and we include that, well, we just get the complex numbers. And essentially that's the reason why doing this with the complex numbers is not super interesting, because no polynomial is irreducible in the complex numbers. Well, that's not totally true. Every polynomial factors into linear factors, but once you factor it into linear factors, you're not adding anything new, so you don't create anything bigger. Okay, so now let's look at this. So x squared minus 2 in Q adjoin x. So So I think we can see that this is irreducible because the square root of 2 is not a rational number. And the square root of 2 is a root here. Now we could adjoin the square root of 2 to q like we did before. Notice the square root of 2 does satisfy this equation. So maybe adjoining it to this, we would have something called like q adjoin square root of 2. And that would be everything of the form a plus b root 2, where a and b are now from rational numbers. And so this is some field that's between the rational numbers and the real numbers. Sometimes we draw this like kind of tower of fields diagram. So we've got q, and then above it is q adjoin root 2, and then way above that is r, and then even further above that would be c. So that's like a pretty common diagram actually. And now let's go ahead and check that this has an inverse. You know, on the last board when we were doing things generally, we didn't like check things had inverses, but now we'll do that because it's a little bit simpler to work with. And the idea here is to look at the object 1 over a plus b times the square root of 2. This would be the inverse if we looked at it in the real numbers, but now we just want to make sure that it's also in this set. And we'll perform a similar calculation to what we did with the complex numbers, and that's multiply by a nice version of 1. In this case, it'll be a minus b root 2. So now multiplying that out will leave us with a minus b root 2 over, let's see, it'll be a squared minus 2b squared. But what does that tell us? That tells us that a plus b root 2 inverse is in fact equal to a over a squared minus 2b squared minus b over a squared minus 2b squared times the square root of 2. So everything that's non-zero does have an inverse. You might be worried that we're getting 0 in the denominator right here, but notice that thing being equal to 0 is equivalent to the square root of 2 being a rational number, which is definitely not true. Okay, now let's look at an example with finite fields. So let's take the polynomial x cubed plus x plus 1 in z2 adjoin x. So that's the finite field with 2 elements. And that's irreducible, well, because it has no zeros in z2. If you plug in 0 into this polynomial, you'll get 1, which is non-zero. If you plug 1 into this polynomial, you get 1 plus 1 plus 1, which is 1 again inside of z2, which is not equal to 0. You might think that the way to find if a polynomial is irreducible is by seeing if it has zeros. Well, that's not true. It's just that that works with degree 2 and 3 polynomials. Now, you could imagine a degree 4 polynomial with no zeros that factors into 2 degree 2 polynomials. In fact, that happens in the real numbers. The polynomial x to the 4th plus 1 factors into 2 quadratics. That should be on the screen right now. But x to the 4th plus 1 does not have any zeros inside of the real numbers pretty clearly. Okay, so anyway, let's get to this construction here. So let's take alpha to be our symbol such that alpha cubed plus alpha plus 1 equals 0. But notice that means that alpha cubed equals, well, negative alpha minus 1. But we're inside of z2, well, our coefficients are inside of z2, so negative alpha is the same thing as positive alpha, and negative 1 is the same thing as positive 1. So this is equal to alpha plus 1. Now we can look at z2 adjoin alpha, and there are exactly 8 elements in this set. And we can write them down pretty easily. So we have 0, 1, we have alpha and alpha plus 1. Next, we have alpha squared and alpha squared plus 1. Notice we do require the square of alpha. It's just once we hit the cube of alpha, we can write it as lower order terms. And then there are 2 more. There's alpha squared plus alpha, and then there's alpha squared plus alpha plus 1. So those are our 8 elements. And now really, in order to check that it's a field, we have to find inverse pairs for all of them. Well, let's do a couple of calculations, and then I'll let you find the inverse pairs if you want to. Let's, for example, multiply alpha plus 1 with alpha squared plus 1. So this is like an example calculation. So let's put here example. This is just like getting a feel for what's going on here. Okay, so multiplying this out, we'll have alpha cubed plus alpha squared plus alpha plus 1. So like I said, that's from multiplying it all out. Okay, but now notice that we can take this alpha cubed and rewrite it using this formula up here. So that turns into alpha plus 1 plus alpha squared plus alpha plus 1. But notice alpha plus alpha is 2 alpha, but 2 is 0 in Z2. 1 plus 1 is 2, which is also 0. And that leaves us in the end with alpha squared. So there we have alpha plus 1 times alpha squared plus 1 is simply alpha squared. So I think that's pretty interesting in its own right. Okay, let's do one more calculation. So let's maybe do alpha times alpha squared plus 1. So distributing this out, we get alpha cubed plus alpha. But now alpha cubed can be replaced just as we did in the previous example. That can be replaced with alpha plus 1, and then we have this plus alpha coming down. But then alpha plus alpha is equal to, well, like we had before, that's equal to 0 because that's 2 alpha. So we have that product is equal to 1 in the end. Oh, but what does that tell us? That tells us that we found an inverse pair relationship. So alpha and alpha squared plus 1 are inverses of each other. In other words, we have alpha inverse is alpha squared plus 1. Great. So there we've got, like I said, an inverse pair relation. So now let's go up here to our set and notice because of this, we can see that alpha squared plus 1 and alpha are inverses of each other. So I'll underline them in the same color. Then maybe very, very clearly the number 1 is its own inverse. So I'll underline that kind of on its own. And then since we're so close to the end, let's see if we can hunt down another inverse pair. Okay, so for our next example calculation, let's look at alpha squared plus alpha times alpha plus 1, like that. But notice that I can factor an alpha out of this, and that'll leave me with alpha plus 1 times alpha plus 1. But now there's this really great trick when we're working in Z2, and that is if you square a polynomial, you just have to square each term. So this in fact quickly simplifies to alpha times alpha squared plus 1. But our previous calculation showed us that that was equal to 1. But that in fact means that we found another set of inverse pairs. Alpha squared plus alpha and alpha plus 1 are inverse pairs. And perhaps we would write this as alpha plus 1 inverse is equal to alpha squared plus alpha. Okay, so maybe we could underline these in the same color. So here this and this are inverses of each other. And now all we have to check is that these last two elements are inverses of each other. Well, I guess they could be inverses of themselves or self-inverses. So let's hunt that down and see if that's not true, then it has to be the other one. Let's do that by focusing on alpha squared. So if we take alpha squared and we square it, we get alpha to the 4th power. But that's alpha times alpha cubed. Oh, but let's recall that alpha cubed is alpha plus 1. So this gives us alpha times alpha plus 1. Okay, but then multiplying that out, we get alpha squared plus 1. Oh, but that's not equal to 1. That means that alpha squared is not its own inverse. That being said, I think it's nice to see the simplification that we did there. So in the end, we know just by the process of elimination that alpha squared and alpha squared times alpha plus 1 are inverses of each other. So there we've got like a full slate of inverse pair relationships within this new field. And now you can like continue to play this game over and over and over again. And this is like something that I do in my class. So for example, I'll let you work it out, but you could build a new field by taking the polynomial x squared plus 1 inside of z3 adjoin x and doing the same thing. And, well, you can see that x squared plus 1 is irreducible, so this same strategy will build a new field. So maybe like try it for yourself. So you can write down all of the elements and then find their multiplicative inverses. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.